Hi everyone, welcome to today's coding session. Today I'll be solving the subset problem using Python. I will explain the problem, its constraint, and the approach we'll be using. We will explore the two efficient methods, backtracking and an iterative approach. These methods will help us generate all possible subsets, the power set, from a given set of unique integers. As I go, I'll explain each step in details. And here is a quick preview of what we're covering, which this tree we'll be using for backtracking to show you as we recurse and as we backtrack. And this is another example display of the same problem, given three numbers. So we are given a list of unique integers and need to find all possible subsets, the power set. The order of subset does not matter, but there should be no duplicate subsets. So key questions here. Are the numbers distinct? Yes. Is the order of subset important? No. We can return them in any order. Should we include the empty set? Yes. The power set always includes the empty set. So here are two examples. So we got nums 1, 2, 3, and the whole goal is to put it this way. And I'll walk you through the detail on how we do that. Same thing, example 2, num equals 0. And at the very minimum, we're always going to have the empty set. So there'll be 2, the empty set and 0. So now that we understand the problem, let's think about the constraints. We can have at least one element and the most 10 elements in the input list. Since the number of subset grows exponentially, 2 to the n, our solutions will efficiently handle up to 2 to the 10th, which is about 1024 subsets. Each number in the array is unique and falls within the range of -10 to 10. This means we don't have to handle duplicate elements, and the values remain small, making subset generation manageable. So this is the big algorithm that we're doing. We generate subsets by either including or excluding each number recursively. First, we start with an empty subset. Then for each number, we have two choices. We either include it in the current subset or exclude it and move to the next element. We'll continue this until all elements are processed. That's the whole algorithm. And that's how we manage to generate. We start with the empty set. Then we go and add the 1 to it. Again, empty set. We already have the 1, so now we're adding 2 and 1, 2. And again, we already had all this, so we're pretty much just adding the blue part. And that's how we generate it. So the bigger the number, so if you go 1, 2, 3, 4, this will be bigger. So it grows exponentially. And this is how we form it by backtracking and recursion. And this is another example of how we do it. So here's the Python implementation. We're going to go and create the actual recursion call, which we call backtrack. I'll have a start and I'll have a path. Then this is what we're going to use to store the results as we do the recursion. By putting it this way, path, in this manner, we're copying whatever is in the content to result, appending it to the end. And now we're going to loop, and we're going to get the len of nums, which is the array here that we're being passed. It can have 1, 2, 3 as the example that we did, and we'll walk through later on as well. And then we backtrack, and we have I plus 1. Then we got the path. So this right here is showing that we're incrementing our level. So we start at the base, the root of the tree, and every time we do backtracking, what we end up doing is we end up increasing it by 1 level, going back up. In this case, this will be recursion. Once we're done with doing the recursion, this is the actual backtracking. This is where we end up going back up the tree by popping the path that we created. This will remove the last element of that of this array. And then once we're done here, we're going to return. But this is how we started off. First, we started off by initializing results. So now we know that results going to be an array. And here is where we're going to call the backtrack. We're going to initialize it to 0. And then we're going to return the result. So once we're done with all the backtracking, this should be the result. Now let's run it. Okay, I forgot to append, which was important. So I need to append num I, and this is where we include the number, since we, as I said, we either include or exclude. So this is being included, the number that we're working with, and this is excluding the numbers that we're working with. Okay, so let's see. So, and the reason we had the errors, because obviously it was an empty list. There's nothing to pop. And as you can see, runtime wise, this is very efficient. Memory wise, not so much. So now let's go through an example problem. So here we initialize the array, as mentioned, and this will be the empty set. Then we're going to call backtrack. Now we're going to append it with the empty set, because the path itself currently has the array currently has no value in it. So the empty set is what's going to be given. And here's what it looks like on a tree. Now we have for I in range, which is going through the loop, initializing it to 0. And the length of num is 3, so our range is going to go from 0 to 2. So now we're adding the value 1, which is what we have stored here, when we go at index 0. So now we're going to start our first backtrack. I was 0, plus 1 equals 1. And path already has 1. So now we got a result. And here we go. So now we appended 1. So now we just did our first recursion. Again, we're looping. We're going to append the next value, which would be 2, I being 1. And we're going to do our backtracking again. So now we're at position 2, and we have the path with 1, 2. And now we are back to appending the value of path to results. So we got empty bracket and 1, 2. And this is where we're at in the recursion, highlighted in red. Again, we're back to the for loop. We're at 2. And then we're appending 3 to path. And we're going to do the same thing. We're going to go back to results. And now we're down to the depth. This is as far as we'll go recursion wise. So, and that's just because it's only goes up to 3 numbers, 1, 2, 3 in the example, as you can see for nums. Again, we're going through the for loop. Then now we start popping. And that's because we already exceeded here. The for loop is 3, which is greater than the length of num, which is 3. But since we're using range here, range only goes up to 2. So that's the reason this returns false. And the only other option we have is to just now exclude numbers from the list. So now I equals 2, and that just means that now we're backtracking. Again, because we increment every single time, when it comes to the for loop, we were at 2 before, and now the for loop went up to 3, because we're going a second time to the for loop. And now we pop out the number 2 from it, leaving the path with number 1. So now we just excluded 2 numbers, 3 and 2. And again, that means in our tree that we recursed back or backtracked back to our previous level. Now we're at 2 on the for loop. So now we're able to actually append the value at 2, index 2, which, as we can see here, index 2 is 3, which is what we got here, and we're appending it to path. Now we're going to backtrack, which means we're going to do a recursion, and we're going to add it to the result, and that's what we got, a new node to the right. Again, we're going to the for loop, but the problem in this case is that the value is higher. 3 is higher than 2, so we're going to have to pop again. And we went from where the path had a 1 value, which was here, and now we ended up being over here. Now we're back in the for loop, now being 1. At index 1, we got 2, so we're able to append it. And again, we increment from 1 to 2, and we are going to add that to result, and now we just created our new node. We're going to proceed again with this. We're at 2 still, so it's still valid. And now we're going to add 3 to it. So now we got 2 and 3 that we add to the path. We're going to do recursion, add that result to our result array. And now we have our new node here. Again, we're going through the loop. That loop is the 3 is higher than 2. So because of that, now we're going to have to remove 3. So now we got 2. And that just means that we're backtracking a level. Again, our previous number was 2, so now we're at 3 in regards to the for loop itself. So that doesn't meet the requirement being 2, so we're going to remove 2 again. So now we got an empty array for path, and that means we're back to the root. Again, then we start with our for loop, which is at 2, so now we're going to be able to get 3 here in the path. And now we're going to do our recursion, add it to result, and this is where we're at. We added 1 node. Again, we're in a for loop. Now 3 is greater than 2, so this for loop will be done. The path is going to be empty at this point, and we're back to root node, which means we cover all possible locations in the tree, and now we're going to return. So now we're going to return the result, and that's it for our recursive backtracking approach. I hope this walkthrough helped you understand how to efficiently generate a possible subset using backtracking. If you found this useful, don't forget to like, subscribe, and hit the notification bell for more in-depth coding tutorial. Now let's explore the iterative approach. So now instead of using recursion and a call stack, which we were using when I was showing you the tree, we'll optimize our solution by iteratively generating subset using a loop-based approach idea. Start with an empty set for each number in nums, add it to all existing subsets to form new subsets. This ensures that every subset is generated without recursion, reducing function call overhead. Okay, so now let me show you the code for this one. So now there's no recursion call, so here we're going to initialize result, and it's going to be already including the empty set. Then we're going to create a for loop, and in this case we're going to go through nums, which is the array that we were given with the numbers. Now we're going to create another for loop, but this will be a list comprehension in order to build our power set. So we're going to call it current, and we're going to add it to the value of num, our current value of num here. And now here's a list comprehension, which is going to build the power set given the num that we're currently working with. Then we're going to return it, and as you can see, this code is there is no backtracking, it's much faster in regards to less code. And let's see how it compares in regards to speed. Okay, so as we can see, it's just as quickly in regards to runtime. Memory wise is just as good as well. So the only reason you want to use one versus the other is if you want to avoid creating a stack overflow or so, if the number is bigger. I think in this case the reason why memory isn't as bad is just because the numbers are constrained per the description. They're constrained from -10 to 10, so if the stack got even bigger, it would really make a difference. So that's probably where the difference is made here. All right, so let me give you an example walkthrough. So first we're going to initialize the result. Then we're going to go num1 is the first number on the list. Now what we have here is current is the empty bracket, and we have num1, which is just 1. So when we add them together, 1 plus the empty bracket is going to give us 1, and that's why we got that. Now we go back to the for loop. We return here now the same thing, 2 plus the empty will give you 2. And now, since we're going through the list, now we're going to 1 plus 2, and 1 plus 2 will give us this once we combine it, which is we're putting it here. Now we're back to the for loop, and we're at 3, and it always starts with the empty set plus 3, and that gives us 3 here. And then again, now we're at 1, so it'll be 1 plus 3, so it'll give us 1, 3. And now we're at 2 here, so it'll give us 2, 3. And then again, now we're at 1, 2, and we're concatenating it with 3. So that gives us 1, 2, 3, and that will end our loop. So we'll return the result, and that's it in regards to iterative approach. So the iterative approach is both time efficient and space efficient compared to backtracking. Backtracking explores all possible subsets recursively, requiring additional stack space. Iterative subset generation achieves the same big O of 2n, 2 to the n, time complexity by significantly reducing function call overhead, making it faster in practice. Instead of using recursion, which involves function calls in a stack, the iterative approach builds subsets step by step, keeping a track of only the subset generated so far. So here, as you can see, time-wise, they're supposed to be exactly the same, which we saw in LeetCode. The only thing we did not see on LeetCode is that the iterative approach is actually, so here it says backtracking is actually more efficient. It's big O of n. Whereas the iterative approach is actually not as efficient because it's actually using more memory. So it goes to show that doing a recursion on the stack uses less memory than actually storing it into an array. Because the array, as we can see here, backtracking, the array, which is the iterative approach, actually builds upon itself, whereas the backtracking, all you're doing is just building a new node. So this is what conclusion I get from this. Anyways, I hope you enjoyed this presentation. If you have any coding problems that you want me to solve, let me know. Otherwise, happy coding and see you next time.